Hi everybody. We have a couple of AP questions I want to get done. Now, I love how they draw these very creative light bulbs, these very creative resistors as light bulbs. And we want to figure out which light bulb is the brightest, second brightest, and least bright. And what we should really be clear on here is this. When you read the word bright in an AP problem. This is kind of new information, so this is one of those things that I'm kind of covering a small topic in a problem that I just didn't have time to do in lecture. So the idea here is whenever you see the word brightest in an electric circuit problem, brightest relates to power. And again, that is work over time, but in E&M, that's I squared R, which is V squared over R, which is also I times V. So we need to kind of get the power through each bulb. And to do that, let's actually talk about the current through each of the bulbs. So keeping this in mind, let's actually figure out what's going on with the circuit. So we have the 6 and the 12 ohm light bulb in parallel. So what that means is that RBC is going to equal 1 over 12 plus 1 over 6 to the negative 1. And so that's going to give us a combined resistance of 4 ohms. And then we're actually going to have that in series with the 10 volt bulb. So then RABC is going to equal 14 ohms. So now let's go ahead and do a little bit of math to get some of the current. So I total is going to equal 42 volts, the voltage of the battery, divided by the total resistance, which is 14 ohms. And so we're getting 3 amps total going through the circuit. What this also tells us is that the voltage across A is going to be the 10 ohms times the 3 amps, which goes through all of it, which is going to be 30 volts. And then what that tells us is if VA is 30, that tells us that VB is going to be 12 volts and VC is going to be 12 volts since they're in parallel. So now let's get the currents. I through A is going to be 3 amps because V equals IR. So I'm using 30 volts, 10 ohms to get a 3 amp current. I through battery B is going to be 1 amp, through light bulb B is going to be 1 amp. And I through light bulb C is going to be 2 amps. Now let's get the power. So the power through A is going to be 3 squared times 10, which is going to be 90 watts. The power through B is going to be 1 squared times 12, which is going to be 12 watts. And lastly, the power through C is going to be 2 squared, I squared times R, times 6, which is going to be 24 watts. So if we rank the light bulbs from brightest to least bright, it's going to be light bulb A, then C, then B. And when we say justify your answer, what they mean is to show the math work. All right, now a switch. We have a switch and inductor. We're going to close the switch at time t equals 0. Let's get some currents. So since at time equals 0, the inductor from the perspective of the circuit acts like a brake, we know that IC is going to be 0. And then what that means is that IA equals IB. And that's going to equal 42 divided by the combined resistance, which is 10 plus 12. And so that's going to give us 1.91 amps. And then a long time after the switch is closed, the inductor now behaves like a wire. And in that case, after we close that switch for a long time, basically it's going to be C part A for the work. That is actually a legitimate way of doing this. The AP actually does accept that, and you can actually go ahead and just copy these answers and say, okay, IA is 3, IB equals 1 amp, and IC equals 2 amps. And again, that's because the inductor behaves like a wire at time equals infinity. Moving on to part C, it says the potential difference across the inductor is a function of time immediately after the switch is closed until a long time. So at time equals 0, all the voltage on that branch is across the inductor, and then the inductor starts to behave like a wire, so it exponentially dies off. So I'll draw this, and then we'll just kind of die off like that. And of course, we get closer and closer to. Oh, that's bad. I'm going to try to do this a little bit better. So there we go. So we're asymptotically dying off to 0, and so that's how the voltage goes. We're going to do a very similar thing. We have a similar circuit with the capacitor. Now what's going to happen with the capacitor is it's going to do the exact opposite of what the inductor does. So it starts off at a voltage of 0, and then it's going to reach some asymptotic limit right here. So that is part D. And yeah, that's it. And so I'd just kind of be clear that this is an asymptote like that. All right, so that is question number 1 on the homework.